All right, welcome you guys. Let's go ahead and do 5-3. So we're going to learn a lot of logarithm properties today and the basics of it. And then we'll continue to learn more logarithmic properties in 5-4. Okay. All right. So, what is a logarithm? I know when I went through school, I knew how to get the answer, but I didn't really understand what it was. It's basically just an exponent. So let's just kind of read through this and digest this to make sure that we understand what's going on, okay? So it says right here that logarithmic functions are inverses of exponential functions. So we learned about inverses earlier in the semester, and maybe you remember, if this is my original function, then to find its inverse, I just switch x and y. So if you look over here at this spot, that's what we've done. We've just switched the x and the y. And now what we're going to call this is we're just going to call this a log. So this is a definition. You just got to memorize it. When somebody says that thing over there is a zebra, you don't question it. That's its name. So you just memorize it, right? So they've decided to write this in the following way to get the y by itself, okay? So logarithms are just exponents. And to just kind of show you that, if I ask you, let's go through a couple of these really quickly so you can see what I'm saying by logarithms are just exponents. Okay. If I ask you these questions right here, I'm asking you for the exponent. So here's how I would think about this. I would say 2 to what power, to what exponent would be 8? And so the answer would be 3. So you're just looking for the exponent on this bottom number that'll get you this number. So since 2 to the third, that's 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. All right, then the answer is 3. If we go over to this one, we say, okay, 3 to what power? What exponent is going to get me 9? Well, we know that 3 to the second is 9, so the answer must be 2. So it's just exponents, you guys. When you look at it, it's weird because it has this word log there, but it's really searching for the missing exponent on this base that'll get you this other number, okay? And that's what this is saying right here. Okay. All right. Now, in order to find it, this might be kind of helpful. I had a teacher back when I took Algebra 2 in high school that called this the hook method, and I'm just going to take it from him. So, Mr. McCandless, this is a tribute to you here. All right, so the hook method. So you start with the base and you cross the equal sign to get the exponent. So this is going to be 4 to the second power equals, and then you come back 16. So that's our hook right there. You start with the base, you cross the equal sign, and you come back. And in this case, there's numbers here, so you can actually tell if you're right or not. Is 4 squared 16? It is, so this looks good, okay? This is what we call writing in exponential form. And that makes sense. We wrote it as an exponent, so that's exponential form, okay? All right, let's try another one. So if we use the hook for this one, we would start with the base. So we'd say 8, cross the equal sign to get the exponent. So 8 to the 0. Oops, 8 to the 0. Oh my gosh, guys, I can't write today, apparently. 8 to the 0 equals. And then after we've crossed the equal sign, come back, grab that 1. And anything to the 0 power is indeed 1. So this one looks good. All right, let's try this last one. The base is 3, so 3 to the negative second. Boy, this one's a little tougher to digest. Equals 1/9. So this one we might want to think about just to make sure our negative exponents are still there. Remember that if you have a negative exponent, you move it down to the bottom and make it a positive exponent. So this actually does work. This is going to be 1/9. All right. So these are converting logarithms into exponentials. Sometimes we do the reverse. Sometimes we convert exponentials into logs. So we just have to do the reverse of that. I always like to think of it as I've got log, and I know there's 3 blanks, right? There's the base. There's the number on the other side of the equal sign, which we know is the exponent. And then this other number over here, the argument of the logarithm. Okay, so I can see that my base is going to be 3. So the 3 will go down here. And then the exponent on the 3 is a 4. That's on the other side of the equal sign. So that means 81 must be here. And these are just definitions, you guys. So there's nothing to like understand. If you're like, it's not a why question, like why are we doing this? This is just, you know, like somebody said, this is how we're going to draw an A, you know, and you just go, okay, got it. So we're just memorizing these kind of definitions, if you will, or way of writing things. Okay, so I can see on this one that the base is 27. So that's going to be my lower number. The equal sign, cross the equal sign is the exponent, and come back and pick up the 3. Last one. We have log with some base. All right, so our base in this last problem is 2. So I know that goes down here. The exponent's on the other side of the equal sign, and then there's the 1. So this is us converting back and forth between logarithmic form and exponential form. Not too shabby. Okay. Evaluate the following logarithms without a calculator. Okay. So I kind of like to, there's a lot of ways to do this, but I kind of like to make it look like what we were just doing by adding this equals x. And then I just do the hook once I add the equals x. Okay. So I'm going to say 4, cross the equal sign to get its exponent. 4 to the x equals 64. And we just have to figure out what x is. So in my mind, I'm like, okay, well, let me multiply some 4s, you know. I know 4 times 4, that's going to get me 16. That's not big enough. So let's try to add one more 4 to it. So if we do one more 4, yeah, that is 64, right? So it looks like it was 4 to the 3rd. So in our particular problem, x would be 3. Let's go over to this other one. So the first key moment was adding an equals x. So we could use the hook method. So we're going to start with the base, cross the equal sign. So 4 to the x, and then come back equals 4. That one's even easier. 4 to what power is 4? Well, 4 to the 1st, right? Done. So you're just hunting down, like we said, the missing exponent. 4 to what power gets you 4? Over here. 4 to what power gets you 64? Yeah. All right, we're going to progressively probably make these a little trickier. Now, this one's definitely tricky. Okay, so if we add the equals x, this would be 9 to the x, 9 to the x, cross the equal sign, then come back, equals 3. And that one's not at all clear. That you might be staring at going, huh? Okay. So something that I want to point out that I'm not sure if it's common knowledge yet at this point, but the square root of x is the same as x to the 1/2 exponent. These are equal. This little fact is, if you ever take calculus, will be ingrained in your mind, but it's kind of cool to know because sometimes I'll have a calculator or I'll be on the computer typing math in, and the thing will only have like a square root. It won't have like a cube root or a fourth root. And it turns out they're all the same. Like the cube root of x would be x to the 1/3. You know, the fourth root of x would just be x to the 1/4. And so if I'm missing this button on the computer or the calculator, then I can just type it this way. And that ends up getting it for me. But okay, so knowing that, I'm going to claim that the answer is a 1/2 because I can see that I'm just square rooting the 9 to get 3. So my claim is that the answer is a 1/2. So if you have 9 to the 1/2, I just got done telling you that means it's the square root of 9. And so the answer is 3. Okay, now, if you're not spotting that, that's what I'm hoping that you spot that right away. That's the quickest way, the most efficient way. But let's say you're not spotting that. Here's an alternative way to think about it. Try to write the two numbers with the same base because they are related, right? 9 is otherwise known as 3 squared. So you can replace the 9 with a 3 to the 2nd. And that's going to be exactly the same. Okay. And then once you've done that, Once you've written the 9 as a 3 squared, well, now let's take a look at what we've got. I'm going to add a little 1 here, you guys, just so you can kind of see where we're going with this. The bases match 3 and a 3. So that part's already equal. So if in order for these two things to equal each other, you just need the exponents to equal each other. So I'm actually just going to set the exponents equal to each other and forget about the 3's. And then if we divide by 2, we've got it. X equals 1/2. Okay, so this is kind of like an alternative way to do it if you're not spotting right away that it needs to be a square root, which means 1/2 as an exponent. And we'll use this more too than just in this particular case. Okay, so we basically rewrote with the same base. If this guy's a 3, then I want this one to have base 3. Okay, so 3 squared. All right, well, the 3's you could basically get rid of. We just need to set the exponents equal to each other and solve. All right, D. So we're going to put the equals X, and we're going to go ahead and use the hook method. 5 to the X equals 1. So we have to think 5 to what power equals 1? Well, anything to the 0 power equals 1. Okay. So there's going to be 2 logarithms that are just so commonly used all over the place that we don't even write the bases on them anymore. They're that common. Okay. So there's log base 10 and there's log base E. Now, how do we write these? Well, we don't use the 10 for log base 10. We just write log, and everybody just has to know that there's a 10 down there. Now, to differentiate it from log base E, which is also used a lot, we write this one as natural log. This ln is backwards, log natural, just because the guy who came up with logarithms, Napier, which I believe is French, some Latin-based language. You know how in Latin-based languages like Spanish and French and stuff, you wouldn't say like we say red balloon. We put the modifier first, you know? You would actually say balloon red. If you were like in Spanish, trying to say it in Spanish, right? You'd say balloon and then you'd say like rojo. I don't know the word for balloon. And so that's what's going on here. Like natural log, well, they would say log natural in this language. Okay, so that's why it's ln. If you're like, what the heck, why is it ln and not nl? Okay. All right, so if there's no base on the log, it's a 10. There's ln will never have a base, but you just got to know it's base E. Okay. And these are on the calculator that we're using in the class. They're right here in this region right here. And this calculator is pretty special because it also has this other button where it lets you pick the base, but we'll talk more about that in a second. All right, so we see these logarithms for the Richter scale, for earthquakes. We see them for the pH of a substance. I just was looking at some test results, some blood test results on my son's tests, and it had like a log on there. So we're just all over the place, hidden behind the scenes. All right, so they want us to do these by hand. So we're going to go ahead and have to write in the missing base. Well, this is going to be base 10 because it's log. And don't forget to put the equals X. And now we're all set up to do the hook. 10 to the X equals, and come back and grab the 10,000. So we have to figure out 10 to what power would get you 10,000. Well, it's got to be 4 because there's 4 zeros, right? 1, 2, 3, 4. If you haven't noticed it, let me just kind of point it out and they'll be like, okay, now it's obvious. But 10 squared we know is 100, 2 zeros. 10 cubed, that's 1,000. Exponent's 3 zeros, etc. So the exponent matches the number of zeros. Okay, we're going to have to put in the base on number B, or letter B. Example B, there we go. That sounds best. All right, so we're going to go ahead and hook it. So we got 10 to the X equals 0.01. Now, for some reason, I'm terrible with decimals, so I always convert these into fractions because it's easier for me to see. So I'm going to convert this into a fraction. So remember, this is the 10th place, and this is the 100th place. We're going way back, you guys. Gosh, what was that, like 4th grade? Totally left the building at this point, huh? The hundredths place. And so that means that this would be 1 over 100. That's how I could write it as a fraction. Now that I can kind of see. I know it's going to be some sort of 2 because there's 2 zeros in 100, right? 10 squared is 100. But the only thing is, it's not this. If there was this, then the answer would be 2, would be done. But the 100's in the denominator, right? That means that the x had to be a -2. Because remember what negatives do, they move it down to the bottom. Go back to this example. Where were we? Did I erase it? No, I didn't. Okay. 3 to the -2nd. We did it down here. Well, that's 1 over 3 to the +2nd. And that's where the 9 comes from. So it's very similar to that problem. Once you see the 1 over whatever, you know it's going to have a negative on it. Okay. All right. For this one, we know that the base is e for a natural log. Get your equals x. So this would be e to the x equals e to the 5th. Well, that one's staring at us in the face, huh? This guy's an e and that guy's an e, so the bottoms match. So in order for them to be equal, the exponents, the tops have to match, right? So x would have to be 5. Now, just FYI, for future reference, if you see natural log of e to whatever, in this case 5, natural log and e are inverses, so they will undo each other. So you can cross them off, and that'll be the answer. Anytime we see natural log of e, you guys, boom, cross it off, done. And that's because they're inverses. Okay, so now these are ones where we finally need to start using our calculator, okay? This isn't something that we would be able to do by hand, but I like to try and do it by hand to show you why, okay? Remember what this is asking, is this is saying 2 to what exponent would get you the 5? 2 to what exponent would get you the 5? 2 to what exponent would get you the 5? And as you're going through all your exponents, right, you're like, well, 2 to the first is 2. 2 to the second is 4. I'm getting closer. 2 to the third is 8. I hopped right on over it, right? So what that means is it's got to be somewhere in between 2 and 3, some decimal value between 2 and 3, probably closer to 2, because 5 is closer to 4 than it is to 8, right? So maybe like, I don't know, 2.2, 2.3, I have no idea, okay? 2.1. So we'll go into our calculator to get this decimal value that we would never be able to get by hand, okay? All right, so let's go pull open, sorry, you guys. Let me pull open our calculator. And I'm going to use this one for right now, but a lot of your calculators don't have this capability that this calculator has. That's why I love this calculator. It does so much. Okay, so we wanted to know log base 2 of 5. We said it was 2 point something, right? 2.32, blah, blah, blah. Okay, so let me pull this guy back open. And we had to round to 4 decimal digits according to the directions. So 9 is in the 4th spot. There's a 2 behind it. So we'll keep it in 9. We're not going to round it up. So 2.3219. 2.3219. Oops, dyslexic moment. Sorry, you guys. I have those all the time. Okay. All right. So hopefully you see why, like, sometimes we're just going to be like, hey, use your calculator. I mean, these aren't going to be answerable always with just using our brains, you know, like the last ones were, okay? All right, so knowing that, let's just go in and use our calculators now. And all of these will be on everybody's calculator because this is the common logarithm, base 10, and the natural logarithm, okay? And those are on all calculators, all scientific calculators, okay? All right, so we're going to go ahead and hit log, which is right here, of 0.074. All right, and we got to round to 4 decimal digits. 7 is in the 4th spot. So 6 will round it up to an 8. So negative 1.1308. Negative 1.1308. Let me just double check. I have a terrible memory. Yeah. All right, let's hit log of -4. error. Put this on here so that we would realize we cannot log negative numbers, okay? You can't log negative numbers. Okay, so this would be like undefined or domain error, whatever. Not in the domain. There we go. You can't log negative numbers. Okay, now we're into the natural logs. Let's go find that guy on the calculator. We got a natural log 200. So he's right next to log. Natural log of 200. Okay, 4 decimal digits. 3 would be in the 4th spot. There's a 1 behind it. So it's just going to stay at 3. 5.2983. 5.2983. Let me make that point really big there. Natural log of E. Let's go put it in. See what's going on here. Natural log of E. And then to the first power. We have to put to the first. So that way it stays E. Okay, remember, E to the first power, you can like cover up the 1. Like it's not there. All right. And we just get 1 out. So, makes sense. We just got done saying a second ago that you could cross off natural log of E because they're inverses. So they'll undo each other. So the only thing that will remain is the exponent. Let's just go back and recap because I need repetition. It was this one right here where we had natural log of E to the 5th. And I was like, just cross off natural log of E. Boom, the answer's 5. Well, this one's a little trickier because it's not like the 1 was written there. You had to handwrite it in. But there's always a 1 in the exponent, right? And so this one would just become a 1. All right, let's go check out natural log of 1. Natural log of 1. And we're getting 0 out. Don't have to round on that one. Oh. So here are some basic properties of logarithms. Let's just kind of go through these and look at them. Okay, we're saying right here that these two are obvious if you use the hook. So let's just kind of make sure we understand. If we have log base b of 1 equals 0, we hook it, that'd be b to the 0 power equals 1. And that makes sense. We said anything to the 0 power is 1. So that makes complete sense. So anytime you see a 1 after a log, you guys, you know your answer is 0. We look at the one right below it that they also say is directly from the hook method. That would be b to the first equals b. And that's like, oh yeah, I mean, there's a 1 here on this guy too. So yeah, b to the first equals b. Sure. So anytime that you see the base matching the input into the logarithm, you're going to have a 1 out. Okay. Now these other ones, they say, are from the fact that they're inverses. So let's kind of explore that. Actually, you know, I'm just going to delete this out, okay? Or maybe I'll put it up in the, no, I'll delete that. Okay, so let's read through these, make sure we understand this and go nice and slowly, okay? All right, the 4 on the right makes sense if you remember that exponential functions and logarithmic functions are inverses of each other. When we first started off this section, we said y equals a to the x. His inverse is x equals a to the y because we switched the x and the y, right? Okay. And that became logarithm. Okay. So what we're saying here is logs and exponentials are inverses of each other. Okay? So that means they undo each other. They undo each other. So let me remind you of something. It's been a while, you guys. It's all the way back, I think, in chapter 2. If two functions are inverses, then when we compose them either way, right? F compose F inverse or F inverse compose F, they're going to undo each other and you'll just get X out. This was a property back then, or maybe it was this, never mind, it was chapter 5. What am I talking about? I get my face-to-face classes mixed up with you guys. We just did this at the beginning of chapter 5, right? That when we compose two functions that are inverses, we get x out. When we compose two functions that are inverses, we get x out, okay? So, well, let's take a look at these two functions here. We got f of x, which is going to be log base b of x. We claim that its inverse then is the exponential, b to the x. So the b's have to match. You got to make sure that these match. You couldn't be like, hey, log base 3 of x, its inverse is 2 to the x. No, you've got to make sure the bases match, okay? So this logarithm will be the inverse of this exponential, okay? All right, so let's compose function composition. Let's do it. Let's compose these. We'll do it both ways just to see what it looks like. Oh, why am I using G? It's F inverse, huh? We'll do it this way first, and then we'll do F inverse compose F. Let's straight mark off. Okay. All right, so if you remember, it's always the right one that gets substituted into the left one. So in this case, we would be taking b to the x, and we would be substituting it in for that x right there. So this is going to be, if we were to write it out, log base b, instead of x, we're going to put b to the x. Now, because these are inverses, everything should cancel, and you should just be left with x, according to this theorem up here that we retyped, right? And that's exactly, if you look at just this spot, that's exactly what this one right here is saying, right? Okay, I've got a logarithm. What's inside of it? An exponential. Okay, what's going to happen? They're going to cancel each other out. We'll just get x. All right, let's try it the other way. So the other way, well, now we would be substituting f into f inverse. So this log will get substituted into the x in f inverse. So that would look like b to the, instead of x, it'd be log base b of x. Now, because these functions are inverses, the only thing that would survive would be x. They would undo each other. And so if you look at that, that is exactly what is written right here. Okay, and then they just did it again over here with natural log and e. But that's the same exact thing as this over here, because they share the same base, right? Natural log is base e, and this exponential is base e. So they should undo each other. And we've already been talking about how when you see natural log of e, you can cross it off. So just x will survive. Same thing here, e of natural log, cross it off. Just the x will survive, okay? So anytime you have an exponential inside of a log, or a log inside of an exponential, as long as they share the same base, they will cancel each other out. Hopefully that made sense. Okay. All right, and that's exactly the case here. Let me put a 1 here just to show you. There's a little 1 exponent here. So technically what we have is we have an exponential, right? It's 5 to the exponent of 1. And this exponential is inside of a logarithm that shares the same base. So they're going to undo each other. Bam. And we're just going to get 1 out. Okay. This is the exact same question as A. If the base is 10 on log when they don't write it, right? That's the common logarithm. And it still has the exponent of 1. So since the base matches the base of the log matches the base of the exponential, they're going to undo each other, and you'll just get out 1 again. And this is the third one that's exactly the same. The base for natural log is e, and there's always a 1 exponent. So you can see that we have the same exact base on the log as we do on the exponential. They're going to undo each other. Just 1's going to be the answer. Okay. All right. On this one, if you wanted to, it'd probably be easiest to just add the equals x to it. because maybe you haven't memorized this yet, okay, which takes some time. 8 to the what? 8 to the what gives you 1. So we have to think about what exponent we could put on the 8 to get a 1. Well, it turns out that the answer would be 0. And let's go back and just look at one of our properties just to remind you. It says right here, anytime there's a 1 in this position, no matter what the base, it's 0. That makes complete sense from the example we just did. Okay. Oh, natural log of e, cancel each other out. Bam, -12. It's my favorite problem. All right. Oh, the base of the log matches the base of the exponent. Oh, they're going to cross each other off. 10 is the answer. Man, give me 20 of these. Okay. This one is exact. There's a 1 inside of the log. This is exactly like this one right here. There's a 1 inside of the log. Oh, they have different bases. This one's base 8 on D. Ours is base. Are you able to finish my sentence? Hopefully you are. Hopefully you said E, right? But it doesn't matter what the base is. If there's a 1 in this position, the answer is always going to be 0. But let's just remind you one more time, okay? If you put the equals x on it, this would say e to what power gets you 1? Well, anything to the 0 power is 1. Okay, these are also some of my favorites. They just reversed it on us. Instead of the exponential inside of the log, now the log is inside the exponential. But the bases match. The base for this exponential is 8. The base for the log is 8. Cool. Goners, just the 3 survives. This one's a little tougher to see, but once we write in here that this is the common logarithm, base 10, then you can see you got your 10 and you got your 10. So the bases match. Cross them off. You got a 14. Okay. Nice and easy. So as long as the bases match, they'll undo each other because they're inverses. Okay. So I just took a picture of a couple other calculators that are popular to kind of show you like one of the many pros to this calculator. Over here, if you have this one, here's your common logarithm and your natural logarithm. But these are the only 2 log buttons on this calculator. There are no other log buttons. So what that means is we can only do log base 10 and we can only do log base e. We can't do like log base 2. Okay. Same thing over here. This is a Texas Instruments also, so they have the buttons in the same position, right? Okay. But there is no log on here where it lets me choose my base. Now this calculator is different. I have log base 10, I have log base e, but I also have this log button that lets me change the base if I want to, right? So I'm just going to highlight that button for the Casio users. Let me kind of highlight these, and I'll kind of highlight these, okay? All right. So if you're working with one of these other popular calculators, well, then you're going to have to know this change of base formula. And I'm going to have everybody know it because I am going to put it on the test, okay? But let's say you start off with log base b, but you've got one of these calculators that doesn't have a log base b. Well, then you can always change it to whatever base you want. In this case, base a, huh? You can always change it to whatever base you want using this formula. The 2 numbers that are given to you, you're just going to use those as the arguments inside the log. So the b, the base, it goes in the bottom, and n, that's going to go in the top. So let's kind of take a look at how this works, okay? So log base 3 of 7. Well, you're not going to be able to do log base 3 on those first 2 calculators. They only have base 10 and they only have base e. So why don't we start off by using the common logarithm? Why don't we change these to base 10? So if we change them to base 10, you don't have to write the 10. If you want to write it, you can. But remember, if you don't write it, it's implied. All right, so this base has to go in the base. It has to go in the bottom. And this 7 will go in the top. So we're going to go ahead and go to the calculator. So how you would evaluate it on, those calculators that I just showed you is you can now. You'd be like log of 7 parentheses divided by log of 3 parentheses equals. And now you can evaluate it. On ours, we could do it either way, right? So if we want to know log base 3, we could just hit that button and be done with it. Let's see what the answer is. 1.7712. 1.7712. Put approximately so people know that I rounded, and I just rounded to the same decimal digits it was asking us for earlier, okay? But another way that we could do that is we could say it's going to be log of 7, close your parentheses, that's a big mistake students make, and then log of 3, and this should get me the same thing. There it is. So you can take a log of any base and change it to any base you feel like. And that's what this problem is forcing us to do. We did the common logarithm. Well, let's go in and use the natural logarithm. So if we have log base 3 of 7 and we don't have that on our calculator, okay, we can always change it to natural log, which is on our calculator. And just remember the base stays in the base. And the 7 will have to go in the top. So let's go and see what natural log of 7. Oh, I closed it. Darn it. I hate when I do that. Divided by natural log of 3 is. All right. So natural log of 7 divided by natural log of 3. ln 7, close those parentheses. And natural log of 3. Same answer. So it doesn't matter what base you use. Oops, I don't know why I wrote a 3. It was a 2, right, you guys? That was a 2. Got issues, you guys. I'm telling you. Don't make me your accountant. I'll drop a 0 somewhere. All right. Let's see here. So now we're going to graph some logs. So it says there are many ways to graph logarithmic functions. So how we're going to do it is we're going to start by rewriting the logarithm in exponential form. Because, I mean, we can just digest that so much better. Okay, we're good with exponents. These log things, these are new. Okay. And we're going to do a t-chart, but we're going to pick y values instead of x values. So let's see this in action. Okay. If I asked you to do this, you would be like, what's, if I plug some x's in and stuff. Okay. But the second that we rewrite this, so here's what I mean by rewriting it. We know f of x is really y, right? All right, well, we're going to do the hook method. I mean, I'm going to do it the reverse way, but it's the same idea. You start with the base, you cross the equal sign to get the exponent, right? So it's going to be 3 to the y, and then come back, equals x. If that's weirding you out, then just flip this guy around and put the log on the left, like we've been doing this whole class so far. And then do it this way then. 3 to the y equals x, okay? So it's basically just always start with the base, the exponents on the other side of the equal sign, and come back, okay? So now if I asked you to do this, this would be a lot easier. I'm going to try to write my y a little bit better, you guys, because it's an exponential and we're so used to exponents. Okay. All right. So let's go in here, pick some exponents. Looks like we already did, right? And notice we put them in the y column. I don't want to be putting stuff into this side of the equal sign. I mean, think about how hard that would be. Right? That'd be terrible to try to solve. Okay. We want to take those values and put them in for the y, because that's going to be a lot easier for us to compute. Okay. All right. So that's the weird part. We don't normally pick y values in our t-chart. It's kind of the rarity, but that's what we're going to do in this case. Okay. All right. So let's go through and do all these. Oops. So we got 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the 1, and 3 to the 2. All right, we did this one today, huh? We said move it down to the bottom, make it positive. 3 times 3, there's your 9. Move it down to the bottom, make it positive. That's 1/3. Anything to the 0 power is 1. 3 to the first is just 3. And 3 to the second is 9. Okay, let's try to graph this. Okay, so x is a 9th. Holy moly, that's going to be so small. Like, you're not even going to be able to see that. It's like maybe like right there. And then we're going to go down 2. So I'm going to put it like right here, you guys. Next time I'm going to go over 1/3. So I'm imagining this being divided into 3 pieces. I'm going to go over 1/3, down 1. 1, 0. 3, 1. 9, 2. Now, there is a vertical asymptote. I'm going to draw him. It's the y-axis in this case. All logarithms have a vertical asymptote. There we go. So that's going to be our graph of log base 3 of x. Let's try another one so we get really good at the process. Oh, let me label the asymptote just to kind of. So there's a vertical asymptote. That's a big deal. That would be x equals 0. And all logarithms will have a vertical asymptote at x equals 0, unless it's been translated. So shifted, to the left or to the right. Okay. Log base 1/2 of x. So we're going to rewrite this, right? Y equals log base 1/2 of x. Use the hook, start with the base, cross the equal sign to get the exponent, and then come back. So that is this written in exponential form. We transformed it from logarithmic form to exponent form. It makes sense to pick y values because then it'll be easier for us to do the math. So that's why we picked y values. Let's go substitute these in and see what we get. On any of these things that I'm substituting in, don't worry. You are allowed a calculator in my class. And so just use the calculator, but it will be faster if you can kind of pick up on, on what I'm doing here, and helpful for those of you who are continuing on, to higher levels of math. Okay, so when you have a negative exponent, that's when you move things, right? Like if you recall, this 3 went down to the bottom, and it's actually over 1, huh? And that 1 went up to the top. So you could think of it that way. So in this case, the same thing is going to happen. We're going to move. So it's going to flip. And it's going to be to the positive 3rd power. So the 2 went up to the top, the 1 went down to the bottom, and then once we move, don't forget to change the exponent. All right, so flip it, change the sign. Okay, so then that's really 2 though. 2 divided by 1, that's really 2. So we just have to do 2 times 2 times 2. So that's going to be an 8. 1/2 to the negative 2, flip it, make it to the positive 2. 2 divided by 1 is 2, and 2 times 2 is 1/2 to the negative 1, flip it, make it to the positive 1. 2 divided by 1 is just 2, and 2 to the first is just 2. Anything to the 0 power is 1. And anything to the first power is itself. Look how quick that is, especially if we can get used to it, versus going to our calculator to get all these values. That's fast. All right, so I'm going to graph the ordered pairs. We got 8, -3 for this first one. We've got 4 comma -2. We've got 2 -1, 1 0, and a half 1. Now remember I told you there's always a vertical asymptote at y equals 0, unless we've decided to translate this, shift it to the left, shift it to the right. So here is our vertical asymptote. There we go. So again, okay. Okay. So same thing, except they threw us a little curveball. They didn't give us the base, but we know that the base of the natural logarithm is e. So we got y equals natural log base of x. So when we do the hook, e to the y equals x. So we're going to substitute in y values. So we got e to the -2, e to the -1, e to the 0, e to the first, e to the second. We're going to need our calculator for these, you guys. I mean, I know this is 1 over e squared, but what the heck is that? Let's go find out. Okay, so 1 e is by natural logs, are buddies. Even on the calculator, they're buddies. Okay. 0.135. So let's just say 0.1, because that's all that we're going to be able to see on the graph. All right, now let's do e to the negative first. So that's 1 over e to the positive first. Let's go see what that looks like. And you do have to put to the positive first in there. 0.4-ish, approximately. It was 0.36. So we'll make that 0.4. Anything to the 0 power is 1. E is like 2.7-ish. E squared, I totally don't remember. I think it was like 9 point something. Let's go check. E squared. Just kidding. 7 point something. All right, 7.4-ish is what I'm going to say. Oops, these should all be approximately, huh? Because I rounded. Let me get this extra string marked out. There we go. Okay, let's try to graph this. 0.1, -2. So like right there. 0.4, -1. 1 0. 2.71. 7.42. All right, and we know there's a vertical asymptote at y equals, or x equals 0. So there we go. There's our graph of natural log of x. This is a big one. You could lock this in your brain. Knowing what this graph looks like helped me through calculus quite a bit. I remember just having it memorized was super helpful. So for those of you continuing on, I want to do that. All right, describe the transformations to the graph. So we just graphed natural log of x. It looked like 0.1, -2, 0.4, -1, 1 0. And I don't remember after that. I have to go back and look. 2.71. 2.71. And then the last one was 7.4, 2, right? Something like that. And we have this asymptote right here. I'm gonna make it dashed. This is good old natural log of x, okay? But we want to know, what does this minus 2 do to it? So hopefully you're noticing there's a difference between that and this. This one up here is inside the function. This one is on the back end. I'm just natural logging the x here, and then I'll take away 2, okay? So remember, if it's inside the function, that affects it horizontally. If it's attached to the back end, that affects it vertically. This one lies, and this one tells the truth. So minus 2, you would think would mean to the left, but we're actually going to go right 2. So what we want to do is we want to pick up not just the graph, but also the asymptote and shift it to the right 2. So let me go ahead and draw a new asymptote, because I've been hinting to you guys that it's always 0 unless there's been a horizontal shift. Well, in this case, there has been a horizontal shift because there's something inside the natural log. So some students get confused. If I had something like this, they'll say that the asymptote's at 4. That's what moves it up and down. So if this asymptote moves up or down, it's not going to change that the line is the line, you know? What's going to change where this line is moving this way, right? And so that's why the part that's inside of the natural log is important. That's where you're going to get your vertical asymptote from. Okay. So here we go. I'm going to shift all of these dots too to the right 2. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And now I'll draw the line through that. My hand's covering it so I can't see. There we go. So the blue one is natural log of x minus 2. Don't mind this weird looking graph right here. There we go. Okay, maybe I'll make it a little bit better, a little cleaner looking. I'm gonna get closer and closer, but not touch. There we go. Okay, so I'm gonna make a big deal about the fact that the vertical asymptote has moved. Same deal. We want to look at all of those changes. Now this one's written backwards. I don't like the way it's written, you guys. So let me go ahead and rewrite it like this. There we go. So we have to talk about all the transformations here, huh? Okay. Well, this plus 1, that's going to move it up 1 because it's telling the truth. So plus really does mean up. This negative out front is going to reflect it over the x. And then a half out front, the number out front is what stretches or shrinks it. In this case, it's going to shrink it because it's a half. So we're going to shrink vertically. Okay. By half. All right, so let's go ahead and graph the original natural log, just like we did last time. Okay, gosh, I already forgot. I think it was like right here, here, right here, 2.7, 1, 7.4, 3. Check those. No, 2.71, 7.42. It's a little too high. 7.42, sorry. Okay. All right. So this is good old natural log. I'm dotting it because it's not the final answer. Okay. Remember, you got to do things in the order of RST. RST. We got to do our reflections first. Then we do our stretches and shrinks. And then we do our translate. Okay. So we're going to do our reflection first. So let's reflect all these points over the x-axis. So this point would go right here. This one would go right here. This one would stay. This one would go down here. And this one would go down here. Okay, I'm going to attempt to draw my reflection. Let's label this as negative natural log of x, so we understand that we reflected it. All right, we got to shrink now. RST, use the alphabet. We're going to shrink it. So everything's going to shrink by half. So this pink one that's 2 high, right? It'll only be 1 high. Oh, I shouldn't use that color because you can't even see that. Let me use green. It'll be 1 high. This one that's 1 high, it'll only be a half high. This one that's 0 high will stay at 0. This one that's -1 away will be half away. This one that's 2 away will just be 1 away. So we made it half. So still going up, we still have a vertical asymptote. But we've shrunk it down so it isn't as tall, if you will. Okay. Or isn't as far away from the x-axis is probably a better way to put it. Okay. So just to kind of recap, you're just taking any point, how far is it from the x-axis, and you're halving it. So if it's 1 away, okay, then now it's going to be half away. Or in the case of where it was 2 away, right? This is 2 away, this dot up here. Well, now it's only going to be 1 away, okay? So you're just going in and halving all the distances from the x-axis. Okay, our last thing to do is to translate RST. So everything's going to go up 1 notch. Okay, this pink dot is going to go up 1 notch. No, I'm sorry, we're on the green, huh? This green dot's going to go up 1 notch. This green dot is going to go up, so it'll be halfway. This green dot's going to go up 1. This green dot is going to go up 1, so it'll be halfway. And then this green dot will go up 1. Bam. There we are. Wow, that was intense. I think it's easier on my math lab than me doing it by hand. Holy moly. Okay, so this is -1/2 natural log of x plus 1. Okay. So that black one is your final graph. There's a lot going on that picture. Hopefully you took the journey with me. Oh, okay. And that was our last one. Okay, so remember you got to go in the order of RST, reflect, stretch, shrink, and translate. So we graphed the regular natural log graph. We took it to the pink ones where we reflected it across the x-axis. Then we shrunk every distance by cutting it in half. So if it was 2, it became a 1. If it was 1, it became a half. If it was 0, it stayed 0. If it was 1 away from the x-axis, it became half away. And if it was 2 away from the x-axis, it became 1 away. Then, because of this +1 on the back end, we just shifted all those dots up 1 space. All right, you guys. Sorry to end that on a tough note. I like it when the last problem is simpler because then we all feel good at the end of the video. But hopefully that made sense. And hopefully on my math lab, it's a little bit simpler to put in, you know, so it's not as terrible as like graphing it by hand. All right, you guys, if you need more practice on this, I'll try to make a video on more of these kind of nasty multiple transformations. I know on the homework, I probably didn't put a lot of them. I probably put some where you just did one transformation. I know myself, I probably wouldn't give you a ton of these. Okay, maybe one, and you got to keep you honest, but you know, not a ton. All right, you guys. Well, thank you for joining me and take care.